All right. Welcome, Mark Tommerdahl, to the Nootralize podcast.
Thank you.
Would you please be so kind and start telling us a bit about the device that you have been one of the two co-founders of and involved in the development of the brain gauge?
Yeah, I'll start and give you a little background. I am a professor at University of North Carolina, and I've been at UNC since early 1980s, and I spent many years hunkered down in a lab until, studying how the brain works. And, basically when you're in a lab like that and you think everything you're doing is important, it's really not. I mean, you're writing papers, and you write a really big paper, and 11 people in the world might read it. So who cares? Anyway, around 2004, we started making some revelations about some very robust properties in the brain that could be measured very easily with certain type of tactile stimulation. And in other words, what we do is we vibrate the fingertips, and your percept, or how you feel those things, is directly related to how things go on in the brain. That's not a real shocker, but the brain is involved in processing all senses, but it turns out that the sense of touch is extremely good for delivering very high fidelity stimuli to very specific parts of the brain. And so we started developing this stuff, and like I said, in 2004, 2005, a guy named Bob Dennis moved in across the hall from me. That was very fortuitous because he basically was has a very strong background in electromechanical engineering, and we're both faculty in the biomedical engineering department, though my strength is in neuroscience and his is in building stuff. And he asked, what could he do to help? And I said, well, if we could build a device to deliver 2 points of stimulation, 2 vibrations at the same time that are really high fidelity, because at the time, most of the stimulators that you got were really, really terrible, and they were very expensive. They cost about $30,000-$40,000 to deliver, and that was something that was really not very good. Well, he said, okay, so he said, how could he help? And I said, well, let's build this device. And we tried to get the undergrads to build it, and in his undergraduate design course. And as usually is the case with senior undergraduates in their spring semester, they didn't get a whole lot done. They didn't get anything done. So Bob spent a weekend and built the device, and that was the first prototype of what we have. And fast forward to today, that device that we used then, we used concurrently all the way through while we changed the prototype and kept building out new ones. We have now is something that is about the size of a computer mouse. Now that's pretty impressive considering the very first one weighed about 15 pounds. And we've got it down to where it's very lightweight. It plugs into any computer or any laptop, anything with a USB port. You plug it in, and what it does is it vibrates your fingers. And by the nerves in your fingers project to these two, to very specific places in the brain, and we can cause interactions between those two places and ask extremely specific questions. But the question that we ask people when they're taking a test, the questions are really, really simple. They're questions like, which of the two vibrations feels bigger? Which one came first? Which one lasted longer? But the underlying stimuli that we're delivering can be a little bit more complicated than that. So most of them are sinusoidal. So if you've taken any math or physics at all at the high school level, you know what a sine wave is. And that's the shape of the wave that we send to the fingertips. And there's a really good reason for that. That we spent a lot of years looking at different frequencies of stimulation and how that changes the patterns in your brain. But long story short, what we did is we set up a series of tests that we could deliver with the brain gauge, and basically you take a look at our website, which is corticalmetrics.com, or just find us by typing in the word brain gauge and it'll pop up. But what you'll find is you can track your brain history very effectively. So every year, like I teach a course in undergraduate neuroscience, and we give all the students a brain gauge. And all the students, typically, they also do, they have labs and stuff like that with it, but they all do their own experiments. And every year, they always discover, hey, I got a lot better with caffeine, or I got a lot better with caffeine and sugar, or I got a lot worse with caffeine and sugar, or too much caffeine. So,
Right.
and what you find is you can plot out how good you are at certain under certain conditions. You know, with students, you're always finding that, you know, people do really poorly when they're testing at 3 a.m. because they've been up for 24 hours, or they do very well if they had just woken up and had their first espresso of the day. But basically, the device is sensitive enough because what it's measuring is interactions, and it's measuring at very high fidelity things like other things too, like reaction time, which is a whole nother story, which you should ask me about. But anyway, every year I'm always impressed. Students always come up with ways to self-experiment with the brain gauge that are separate from the labs. And I get a lot of feedback on what kinds of things actually allow them to form what we call a tuning curve. So if you're familiar with a tuning curve, that's basically like a little bit of something might be good for you. Too much of something might not be as good for you. So, you know, let's take caffeine as for example. There's an optimal amount of caffeine, and most of your listeners probably have at one time or another probably done too many shots of espresso or too much coffee or tried to stay up all night, and you find out actually performance is enhanced a little bit with the right amount of caffeine, and actually starts going astray as you get way too jazzed up.
Yeah.
So, and that's one of the things you can actually put a number on with the brain gauge. And we're probably one of the few tools that you can do that with, or one of the few inexpensive tools, I should say. But it is a laboratory grade device that has been converted into something that consumers can latch onto.
Can you please elaborate a bit on that point? Like, how do you measure the quality of the measurements that you're making with this tool?
How do we measure the quality of the measurement?
Yeah, so the reliability and the validity of for example, as you mentioned, you wanted me to ask you about the reaction time measures.
Here, let's go to reaction time. So most people, you know, a lot of your listeners may know that, oh yeah, I can measure reaction time. I can pull up a program on the computer and online, and it'll flash something on the screen, and I'll hit a button and it'll give me a reaction time, and that reaction time will be 300 or 400 milliseconds or something like that. Now, operating systems cause a lot of delays. Keyboards cause delays. There are hardware delays intrinsic in computer mice, and we are about to publish a paper on this actually. But what we did was to do exactly what you're asking, we did some robotics testing. We took the human element out of it completely. And what we found was that competing like other methods, these other methods that are just using consumer grade computers. So a lot of people are using laptops in their labs. Laptops like, well, what everybody uses. And they just think, oh yeah, this is a really expensive laptop, so it probably is going to be really, really accurate. And that is so far from the truth. You know, it's not accurate for reaction time. Just because it's fast doesn't mean it's not going to say, hey, I think I'll take a 30 millisecond nap over here, or I'm going to do something else for 80 milliseconds. And what we found when we did robotics testing and compared the brain gauge to a couple of other methods, like one was doing a visual test and responding robotically to touch screen, and another one was, visual flash and responding to a computer mouse, again robotically, that there were 400 millisecond delays in the touch screen and about 100 millisecond delay with the computer mouse. Now, and there's also been a couple of papers, like I warned you guys that I get off on tangents and I'll talk forever. But there's a couple of, one thing you should know, that you go back and you look at the literature, and there have been papers on reaction time going back to the 1850s. And it's really interesting. So if you go back to the 1850s, 1900s, you'll see reaction time is around 200 milliseconds, for healthy subjects. And so remember that number. So from 1850 to 1970, reaction time that most people saw in the published literature was between 200 and 220. And then all of a sudden around 1970, it started drifting up. And, I've even seen papers where reaction time was over 1 second. So that's like 1 Mississippi. And then that's, you could stand up, sit down, and hit the button. This is like you feel a stimulus, you sit down and you respond. Or you see a stimulus, something flash on the screen, you hit the button as fast as you can. Your reaction time is really, really should be much faster than 1 second.
Right.
So anyway, but there are a lot of publications showing, between 1970 and the present day, where reaction times are not 200 milliseconds. And this is for healthy controls, but 300, 400, even 500 milliseconds. That's really slow. So what could be the problem? And we weren't the first people to point this out, but we just went ahead and did robotics testing on the different systems, and we found, well, these delays are being introduced by computers. So what started in the 1970s? That's when we started having the introduction of personal computers, and that's when reaction time started getting worse and worse and worse. So when we've done over 1,000 people in our healthy control database, and on the brain gauge, and their reaction time averages 210 milliseconds. So right spot on with what people were doing in the 1850s. So there were papers out where people surmised that we were getting dumber because reaction time was getting slower, which I found kind of interesting. But it was the first thing they jumped to, is like, oh, we must be getting dumber because look at how much how slow reaction time is getting. And reaction time has been kind of linked to cognition for about 100 years, certain aspects of cognition. And it's a really simple test. I mean, it's just exactly what you say. But reaction time variability is another test that's really, really extremely accurate, extremely good for looking at things, but you can't measure reaction time variability if your system is inaccurate. And what I mean by reaction time variability, let's say you're taking a test. And let's just say, okay, you feel a tap on your finger and you hit a button. That's your whole test. So if we do it the first time and you feel a stimulus, feel a tap on your finger, and then you respond, and let's say the first time you do it, you'll see it flash up on the screen and says, okay, your result's 200 milliseconds. Then you do it again and say it's 200 again. Well, let's say it's 200 10 times in a row. That means you have a variability of 0 because it's not changing. And you're doing this over and over and over again, and it's really solid. Let's say you're a little distracted and your focus is off, and your focus is not very good, which is obviously something that people want to improve. But let's say the first time you test, you're 240. The next time you test, you're 200. The next time you test, you're 280, 240, 200, 320, whatever. Then your reaction time variability is going to be is going to be computed to be around 40, which is pretty high. And people who are concussed, our cutoff for people who are concussed is around 20 milliseconds. Now, the reaction time variability that we measured on the brain gauge, or the brain gauge was accurate down to 0.3 milliseconds on this test. And whereas the next competitor had a latency of 80 milliseconds. And the variability on these other methods was on the order of 40 to 120 milliseconds. So if you and what we find with people who are healthy, generally they're healthier between, your reaction time variability is going to be between 5 and 20 milliseconds. And our cutoff for one of our papers was 22.4 for concussed. So individuals who are concussed were at 22 milliseconds or higher. So they can't even be detected by other systems. That reaction time variability can't even be detected because the system is so, well, the other systems are just, they don't even report reaction time variability. But you have to have an accurate measure. And the way we do that with a brain gauge is we bypass the computer to do the measures and do all the internal circuitry is on in this device that basically looks like a computer mouse.
Hmm. Could you please describe a bit more in detail why specifically reaction time variability is important?
Well, I mean, you know, if you're, let's say you're driving a car and, you know, you want to react and respond to everything that you process. And I think people take for granted everyday things, you know, whether it's catching and throwing a baseball or driving a car. But you think about it, you drive a car and you see somebody pull up to the intersection and they're supposed to stop, but you say, oh, well, are they stopping? But you do a lot of math in your head just to see people pull up and stop and slow down, and you determine, and you know, or if you're stopped at an intersection, you see an oncoming car, you do quite a few mental calculations just to determine if it's okay to pull out in front of them. So, you know, that's your information processing speed. You take in lots of information, and you need to be able to process it in a fairly, you know, quick manner to be able to determine whether to make, what kind of decisions to make. You know, whether it's just getting out of the way or moving. But reaction time is, you know, it's fairly important indicator. It's an indicator of myelin health. So if your white matter gets degraded, reaction time goes down. If you're on some kind of pharmaceutical, some kind of pharmacological agent, your reaction time probably could go down.
Right.
A lot of people look at, okay, what are the effects of acute alcohol? Well, it does make you slower after you've taken a certain number of drinks or after your blood alcohol content goes up.
Mm-hmm.
But it's a really good first crude measure. It doesn't give you a whole lot of details about cortical circuitry, but it gives you a good robust number about, like I mentioned, the tuning curve. Okay, let's say, what's my optimum performance? And, you know, optimum performance on caffeine. And you drink a cup of coffee and your reaction time gets about 10, 20 milliseconds better. And then you drink another cup and you get either a little better or no change. Third, fourth, fifth cup of coffee, and you start getting, you stay about the same, but your reaction time variability starts wavering, and you keep drinking, and then all of a sudden your reaction time starts getting worse. It's just because, you know, it's not, that doesn't have anything to do with myelin, but it has to do with cortical processing and the ability to focus and to actually focus on the task.
Hmm. So reaction time is more so a measure of cognitive processing speed, whereas
Okay, it's one of the measures that we take, and as we call that information processing speed.
Mhm.
And some of the other measures we do look at things like lateral inhibition or accuracy, feed forward inhibition, which is another function of the brain, connectivity, how well do different groups of cells work together, timing perception, that's related to coordination, how well are the different cell assemblies, the different groups of different regions of the brain working together. And then we also look at frontal parietal brain health in a couple other ways. One is just looking at your ability to determine order. You know, if we deliver two stimuli very close together, can you tell which one came first? And that's actually very related to, you know, like if you get hit in the front of the head, you actually do very poorly on that test. Get hit in the back of the head, it really screws up your timing perception and how well your coordination. It also impacts your coordination.
Hmm.
Did that answer your question? So
Well, I think I haven't asked the question well enough yet, because what I'm actually trying to figure out is what is the difference between reaction time measurements and reaction time variability, and
okay,
how should
reaction
people
time.
interpret them differently?
Sure, reaction time is brute force. How fast can you do something? Reaction time variability is really a measure of focus. How consistent are you? And if you can attend, if you're like people with ADHD do very, very poorly on reaction time variability because they
Mm,
cannot focus.
mm,
Even though their reaction time may be pretty good, it's not consistent because
right,
their mind is wandering and they're always thinking about something else.
right.
So that's the simplest answer.
Yeah. So because the brain gauge is, in
So
your
because the
word,
brain gauge is extremely accurate,
yeah.
and its accuracy for measuring reaction time is 1/3 of a millisecond. It is well beyond the temporal resolution that you need to actually make that measure. And there is no other commercially available device that can do
Mm,
that. And that's because everybody else just uses a computer, which has a lot of inherent flaws because
right.
operating systems introduce delays.
Yeah.
Uh, consumer grade equipment is great. I use computers all the time that are, they're cheap, relatively cheap, but they're not laboratory grade equipment.
Right.
And that's the difference between the brain gauge and everything else, is that it is actually laboratory equipment. It's really like $100,000 worth of equipment that has been crammed into something the size of a computer mouse
Mm,
over the last few years. Now it doesn't cost that much. I mean, we obviously sell it for extremely low price, but uh, we spent a lot of time miniaturizing the device,
right.
and that's all thanks to the Office of Naval Research, who paid for that development.
Mm,
So consumers don't have to pay for the development.
right. Yeah. That's great. Like, you can, I guess, produce it on a mass scale so that it can get cheaper. And of course, as you mentioned, the funding as
Mhm.
well must have helped. So could one say that using reaction time as a measure of focus via your computer is not accurate enough?
Correct.
Yeah.
You really do need to use something like this. And that's only the first measure. The reaction
Right.
time is only the first measure, that the first test that we deliver. And let's talk about a second test
Right.
that
I'd
we
love to
deliver.
do that. Just
Yeah.
before, on the reaction time measure, do
Okay.
you think that the computer tests uh, that people can use to assess their reaction time, can they have any use cases? So is the accuracy enough for any use case?
Uh, they're pretty bad. And one reason, I'll be blunt. So everybody's aware. How many years have you been listening to people talk about concussion and concussion research? 15? 10 or
Um,
15?
can you,
Decades?
can you repeat the question?
Okay, so how many years have you been
Uh,
reading in the general news media about concussion?
well, I'm quite young, so you
Okay.
shouldn't ask me that question.
Okay, so probably your entire life
Right.
you've grown up around concussion, and basically a lot of concussion research is to be quite frank, is terrible. And the reason it's terrible is because the same people do the same research year after year, year after year, year after year, and they continue to get funding. And okay, let's take, for example, let's just strip out everything. Let's say just to compare us to somebody else doing reaction time. Reaction time is one of the components of other tests. So they deliver reaction time test, and it's got all this intrinsic variability in it. So if you collect, say, 1,000 subjects, you will see a difference between individuals with concussion versus healthy individuals in the average reaction time. And it'll be about a 10 to 20% difference, maybe. So, and that's because, and they say, oh, look, we found a difference. This should be a good measure for looking at and evaluating people with concussion. However, let me explain it another way. If you were to go into the doctor's office and they gave you a test and they say, okay, we're going to test another 999 people, and then we're going to tell you what your diagnosis is, how would you feel?
That seems like a strange method.
That's exactly what kind of research is going on now, and has been going on for decades, like at NIH, where they fund concussion research to do this kind of stuff. But, people keep they're not developing translational methods. There's there's market pressures, there's commercial pressures. Some of the, I won't name them, so I won't get sued. But there are other methods out there that are pretty terrible, but because they have positioned themselves in the market, they're used over and over and over by high schools, colleges, pro teams to do baseline testing for concussion and then test for concussion. And, they charge a lot, and they do it all online, and the tests are pretty inaccurate. And basically there's been a lot of papers on a lot of these methods where it's extremely reliable that people recover within 7 days. Play football on Saturday, they're ready to go the next Saturday. How about that? They always recover within 7 days on that particular test. So It's kind of fishy, isn't it? So anyway, the reliability of those measures, we're talking about the problem that we've gotten into is that we're using consumer grade hardware to do what should be laboratory grade testing. If you want to do an accurate test, you need to do something accurately. If you do it accurately, then you say, hey, yeah, you look like you're not in the normative zone anymore, buddy. Your values are way out of whack. But if you do something unreliable, we'll say, yeah, this system's really not variable, but we'll put your name down, and after we collect a few hundred more people, we'll get a good idea about which group category you're in. So that's really not the way to go. So we've spent a lot of time developing tests that allow you that are accurate.
Yeah, I can definitely see your perspective, and I think that your reasoning is sound. I'd love to hear you discussing this with someone who is a developer, let's say, of one of those tests.
I actually have discussed it with them, and they were, some of them are, well, yeah, we know we have problems and we're fixing it. I was like, okay. And I was trying to partner with them and say, you might benefit if we partnered on this.
Right.
And they weren't really interested. So anyway, that was commercial pressure to not partner with us. Right. But that's actually coming back around again. So because, well, that's a long story. Yeah. That's really not suitable for this.
Right.
This mode.
Yeah. Well, so the answer to my earlier question is reaction time useful as measured by online testing and with a normal computer. Are they useful, these measures, for any purpose?
If you're using the brain gauge, it certainly is. It's one of the most useful tests. If you're just using an online test, you got to understand it's so variable. You can take the test 5 minutes apart and you'll get a different answer. So you can
Mm-hmm.
test it yourself. But it's not just that it's adding a latency, it's adding variability so to your answer. So, you could probably, test yourself 1,000 times and get a little better resolution, but that's a lot of testing. So my answer is not really. I mean, we've seen these tests over and over and over again, and it just they're just not that good. Okay, so what we're talking about, you're talking to a researcher, somebody who spent his life doing research, and talk about doing research with laboratory grade equipment that you spend time calibrating with versus stuff that has an enormous amount of variability in it, enormous amount of error in it. But, if people want to do that, that's fine. They can get the most expensive tablet and then do a reaction time test on it, and it's going to be inaccurate because of all, especially with a touchscreen, it's really, really inaccurate.
Mm.
And, it's not going to tell them a whole lot.
Mm.
Sorry, I wish it were not the case, but
Yeah, of course.
That's a state of, and that's sort of something that I'm somewhat passionate about.
Yeah.
Well, but yeah, go ahead.
The reaction time, for example, the simple reaction time measure, that test is used quite often in studies on nootropics.
Mm-hmm.
So in placebo-controlled studies on these compounds, they
Right.
are used. Do you know if these results that we can find in these studies, then are they reliable?
Yeah, I mean, like I said, if you're doing group studies, you'll see individuals. It's like you can see differences between the groups, but if you want to see really accurate results, you need to use really accurate methods. Now, some of these studies, if you look at them closely, they are using accurate methods because they're not using you can build your own reaction time devices. I mean, it's a little harder to do it commercially, but you can build a fairly accurate reaction time device. It depends on, it's a case by case basis on study by study. But like I mentioned before, it will show differences in group and populations. If it shows a difference in the populations, then it's meaningful. But it probably would have shown a much bigger difference if they'd used a really accurate measure. And it just really depends on what they used. If you look at the paper and it says, okay, a reaction time was collected by a personal computer, yeah, probably they just sort of, who knows what they did. If they use some other system, there are some systems that if they used a system that they built in the lab to test, then it probably is accurate. So, and you have to, but when you do an experiment, you calibrate your equipment. This is something that we did routinely in the 1980s, 1990s. Oh, and even now, we still, and people have been doing this for decades. Calibrate your equipment every single study. Don't just say, oh, operating system, this program told me reaction time was this. But on average, if something works, like for concussion, which is the opposite of nootropics, people that are concussed, their reaction time is slower, no matter what system. Problem is you can't measure reaction time variability, and you can't get a really good feel for just how big the difference is.
I see. Do you want to go into another measure that one can get from using the brain gauge?
Sure. So one of the things that we look at is we basically call it accuracy, but it's one of the things that's really interesting is first concepts one of the first concepts in neurophysiology that we work with. It was started back in the 1950s and 60s by a guy named George von Bekeschi. And he proposed the idea of something called lateral inhibition. And lateral inhibition means basically if you have an area of excitation, if you excite one area of the brain, then the surrounding areas are inhibited. Now, he made this proposal all based on his observations of sensory perceptual tests. So he did tests with sense of touch, vision, auditory, taste, and smell. And through this, he found this one thing that was consistent was that you have this you turn something on in the brain and it automatically turns things off next door. Well, so that's a really, something that we spent a lot of time investigating for a number of years. But one way to test that is simply if you deliver, so if I deliver a stimulus to one finger, it projects to a place in the brain, it activates that spot, and what do you think happens to the place next door to it, like where the other finger projects to?
Well, based on what you said, it would shut off?
Yeah, it would try to turn it off.
Right.
Now, if you deliver those two stimuli at the same time, you're activating two places, and it's going to try to turn off the area in between. So if you, and when your brain is healthy, you have no problem telling the difference between those two. So that's called amplitude, and the way we test that is called amplitude discrimination. We deliver stimuli of different amplitudes. So if we deliver two stimuli at the same time, one is a little bit bigger than the other, let's say, what's going to happen to the smaller stimulus is that the smaller stimulus, just like you mentioned before, the bigger stimulus will win. The bigger stimulus will turn off, will be more successful at turning off the smaller stimulus. The smaller stimulus isn't excited enough to turn off the big one.
Mm.
That is what allows you to discriminate between two things. That's one of our accuracy measures.
Mm-hmm.
So, and that turns out to be an extremely good measure, extremely indicative of things. Basically, it's indicative of or correlated with GABA. And GABA, you guys may be familiar with because a lot of nootropics target GABA,
right,
or mimic it, or mimic or some kind of GABA agonist. But GABA is the most prevalent inhibitory neurotransmitter in the brain. And when you turn things, and basically, if you don't have enough GABA, you can't perform that test very well. Now, what we do is we do the test twice. In the first test, we do its amplitude discrimination sequentially. In other words, we deliver one stimulus to one finger, then we wait, and we deliver another stimulus to the other. And we see how good you are on that. Then we deliver both at the same time. And if you should perform about the same on simultaneous versus sequential. In other words, you deliver two stimuli at the same time, where one's bigger than the other, and you should be able to tell which one's larger because your brain is working properly. It's turning things off when it's supposed to. Mm-hmm. And you do the other one sequentially, basically that you should be the same, because when it's sequential, lateral inhibition doesn't play that big a role. Okay. You can automatically feel those two stimuli and sort of remember which one's larger than the other. Mm-hmm. And so anyway, when you're healthy, your results are about the same for those two tests. Now, when you're unhealthy, or say this could be a lot of different, let's call it a neurological insult or a neurological disorder. A lot of those are very much GABA deficient. Concussion is one of those. You have hyperactivity in early stages of concussion. You have hyperactivity in autism. you have changes in, in these activity levels with ADHD. Just about every neurological disorder, you'll see a slight difference in your ability to discriminate between those two places, and the difference between sequential versus simultaneous will change. So that's another test that's extremely useful. It's very powerful, and people like to see, can they improve that with systemic alterations? Again, alcohol is a GABA agonist, so but it's also an antagonist of other things. And initially, it actually improves your score slightly, and then you start getting worse.
Right.
At least that's what we seem to see in a lot of people's acute alcohol studies.
Mm-hmm.
One or two drinks, and you tend to perform just a little bit better on one test, and then after that, you start getting a lot worse. So.
Yeah, I talked with Professor Andrew Scully about that, actually. Do you know who he is?
No, I don't.
He's a researcher at Swinburne University,
Mm-hmm.
and he had done a study on the effects of low doses of alcohol on memory performance, and also found that low doses can actually enhance your memory performance.
Mm-hmm.
Yeah,
it's really interesting. And a lot of people have the misperception that alcohol improves all kinds of performance. Like, they'll think, hey, I can lift a lot more weight after a six-pack. And, if you call them on it, you find out they can't. They just have the perception that they're stronger.
Right. Yeah.
Or that their reactions haven't changed, but they certainly do after a certain number of beers.
Right.
I have performed the test on myself, through a number of drinks, and found that, I did get better after two drinks, and then after several more, I kept getting worse and worse.
Right.
So there was no turning back.
Yeah. I see. It does seem like you do need to understand some neuroscience, perhaps, but also some.
It's actually, we've set it up so that it's really very easy.
Mm-hmm.
It's a self-administered test.
Tell me.
And it's very easy to perform. We've got we work at a lot of military places, and we work at, like, with people doing sports concussion. We work at a lot of different clinics, and for the most part, if you just want to measure your performance and track your performance, it's really, really easy to see that you're getting better or worse, because of something. And it's sort of science made easy. And if you want to read more and read about each measure, you just click on the measure, and it'll tell you, where to go to read or what that measure is. And then we have articles on each measure. But it's made so that you can get by on very little knowledge of the science. But most people do want to, sometimes they want to learn more. They say, oh, I've got a deficiency on this score. What should I do to improve that? And, sometimes it's, we don't make any diagnostic claims or anything like that, but we just say this would be consistent with improvement might be with, say, some type of nootropic or some type of GABA agonist, or whatever. But it's very simple to use. And the reason it's simple to use is because we're lazy, and we don't want to have to spend all our time on the phone talking with everybody that uses it.
Right.
Operators in Germany right now, military operators in Germany really like it. They love it better than all the other tests they take. The other tests they take they got tired of. But this, they can see their results right away, and they can see how they're improving until they're ready to return to duty. We test people who've been exposed to blast and have, mild head injuries, and it takes them 2 to 3 months to fully recover. So, they can track their progress. But, and if they do anything different, then to try to accelerate their progress, we can see that as well.
How useful is the brain gauge for healthy people? You've mentioned a lot of use cases for people with diseases or head injuries, but how useful is it
Right.
for people using nootropics, for example?
Right. So it's very useful for tracking your brain health, and your brain health fluctuates daily. A little bit. I mean, when you have a concussion or brain injury, it's going to fluctuate 1, 2, 300%. I mean, it's going to be real significant. But, if you want to see, what are the effects? Are these nootropics working? I get this question all the time, is like people taking supplements and they say, hey, do these supplements do anything? I say, well, you need to find out. And they find out that sometimes they are doing something and sometimes they aren't. So that sometimes they're improving their brain health and sometimes they're not. There's a lot of people want to, just say, well, they're trying different things to improve their brain health. And if you're trying to improve your brain health, you really need to measure it, because self-perception is a terrible measure. It's like if you want to lose weight and you don't want to weigh. I mean, you basically you have to have some objective way. And if what you're doing is using your brain to measure your brain, if there's something, basically your perception of your brain performance is always different from what it actually is.
Right.
So the only way to really know whether you're on top of your game is actually to measure. And nootropics are going to be like anything. Every nootropic is going to have a tuning curve. And, people wonder, well, if a little bit is good, is a little bit more better, is a lot more better. And so at what point do you know that you're taking too much or the right amount? There's an optimum amount for everything. And the only way to really know that is to measure it.
Right. Do you have any statistical analyses of the results to give users of the brain gauge answers to whether a nootropic intervention, for example, is effective, like pre and post comparison, or is it just a visual inspection of the graph over time?
Okay, so sort of two different questions.
Right.
One is, yes, we have about 80 publications right now. A lot of the reports on nootropics were basically done as internal reports or people telling me whatever. Basically, they're small research reports that aren't published. So those are things like caffeine, walnuts, chocolate. All those things have been exhaustively studied and show improvements in some functions, not in others. But the nice thing about this is, because it's tracks against a normative database, it's really easy to just use your own data as a case study. And basically just plot your own brain health along time and see whether improvements are made. And it's gives you a pretty good range. You can say, okay, this changed results by this many standard deviations. And that's, this improved my scores 40%. And that's really the way most people are using it. Most individuals are using it. Clinicians are using it to say, look at this. Oh, well, this, I've been trying this treatment on this guy for a while. Let's switch treatments. They switch treatment and all of a sudden the person gets better. It's like, or slowly starts getting better. And they say, oh, I'm going to continue with that treatment. So you don't have to be part of a research study to show that it's effective. But we've done enough, we're involved in enough research studies around the world to know that it's in a lot of different type studies to know that it's a very effective tool for measuring subtle changes in brain health. And if the nootropics people are using are actually changing their brain health. They should, if they really want to see it, they need to baseline, and then baseline without the nootropic, or test themselves while they're on the nootropics, and then baseline off it and see if there's a difference.
Right.
So,
but when they do that experiment, do they, in the brain gauge user interface, do they get a graph, or do they get
there's
numbers?
a graph, and if you go to the website, you can see what I'm talking about. But there's a time course graph, and also you can print out a report for each session, individual session. But you don't have, the more data points you have, in other words, the more times that you test over, let's say you test 5 times or 10 times in a month, or that many times in a week, like some people do, and depending on, and you can actually add notes. It's like, okay, so where did you not have, where you had poor sleep habits, or where you had a stressful day, or where you started taking some type of nootropic, and you can add all those notes in, and it'll show up on your chart. It'll show up on the graph. So there's a historical plot that shows your progress that you can refer to anytime.
Right. Are there any numbers? You mentioned standard deviations. How do people get
Well,
access to that?
the way, most people aren't scientists and
Right.
don't think in terms of standard deviations. So
Yeah.
what we do is we plot it in terms of 0 to 100. So all the numbers are plotted from 0 as being bad to 100 being spot into the normative range. And, and if you, say you drop down to 80, that means you're 20% below the normative range. So, which is roughly 1 standard deviation. But most people prefer to think of it in terms of 0 to 100. That's much easier for most people. So it is the raw numbers are available and also show up on your report. So let's say there are a few people that are shooting for 110%, and they can still see their numbers improve if they're better than the norm. And so that's totally reasonable for people to do better than, a lot of people that are healthy are always trying to get a little bit better than whatever the norm is.
Yeah. You mentioned caffeine, alcohol in low doses, walnuts, and cocoa. Are there any other interventions?
GABA comes to mind as one that we have a study that looked pretty good. Ozone therapy, that's not really a nootropic. Hyperbaric chambers, those aren't oxygen therapy. A lot of people do sleep in. I know a lot of triathletes who use like tents, for altitude training, and those also seem to have an effect. What else? I've seen different supplements. Ginkgo Biloba is how do you pronounce that? Ginkgo is one.
Yeah, Biloba.
Obviously, people have done lots of sugar, different vitamins, a lot of different supplements. But it's all it's basically, we've even seen results. We've seen results with meditation in actually measured effects of meditation or mindfulness, which I know is not a nootropic, but just to give you a sense of the sensitivity of it.
Yeah.
So it's fairly, it's a very good measure for overall brain health. And if your overall brain health is improving, then from nootropics, then you should see some kind of changes.
Right. So you've done studies on the effects of mindfulness with the brain gauge tool?
Yes.
Okay.
Yes, we have.
Cool.
Those aren't published yet, but we've got accumulated quite a bit of data. That's pretty solid.
Would you mind sharing a bit?
Well, basically, we did a modified protocol. Normally, we do about 7 or 8. We recommend 7 tests, but at this particular doctor's office, we focused on the tests that were most sensitive to stress and anxiety. She had a lot of patients who had stress and anxiety from pain. Okay. So the subjects came in, or the patients rather, they were tested, and then they had a 45-minute, I guess you would call a relaxation session, mindfulness, meditation session. And then 45 minutes later, their scores improved by 40%. So that's fairly significant.
On these 7 measures?
No. Overall, we cut the test down to just 2 of the score, three of the tests out of 8, and just to so we have, because they wanted to make it short, make it 5 minutes. Taking all the tests takes 15 to 20 minutes. We wanted to do something in 5 or less. But on those tests, we saw a 40% improvement.
And what cognitive functions were measured?
Yeah, they were basic. The ones most related to stress have to do with frontal parietal function, and the tests that we do there that are most sensitive to that are temporal ordered judgment, is basically your ability to tell which of 2 stimuli comes first, which seems very strange that you would say, well, how do you know that's in the frontal lobe? And the way we know that is because we've done studies where we block different parts of the brains with TMS. So I don't know if you're familiar with that, but that's a way to actually turn off part of the brain and then see how you still perform on a test. That's how we do know different areas work. Anyway, those tests were that 40% is a significant change.
Right. So that was like for stress, anxiety, temporal order judgment, and some other ones together, like a total score. Right. Cool. I'm looking forward to reading that study. When will this be published?
I don't know. The study was being done in another country, and we've got about 40 data points, which is more than enough, but COVID yanked that particular clinician out of their normal role.
I see.
And so they are dealing with a lot of COVID related issues with their patients. Basically, I have two colleagues that are in different parts of the world that got yanked out of research completely because of COVID.
I see. That's unfortunate.
Temporarily. So, I mean, just still doing their clinical duties, just don't have time to write up papers.
I see. Where can people buy the brain gauge online?
They can buy it online at our store, corticalmetrics.com. If you can't remember that, it's you just type in brain gauge, and that will pop up on the first several listings. And it's easy to find. Just type in the brain gauge and it'll take you to the store.
Right. We will link to that in the description of this podcast. You mentioned something.
And, we have a discount, a Nootralize discount set up for you guys.
Right. Yeah, I appreciate that.
Okay, well, great. It's been fun talking to you.
And to clarify for the listeners, the discount is our
20%.
name.
Yes,
20% and our name.
Yes, your name.
Yeah,
Nootralize.
Nootralize, yes.
Yes.
Yeah. Thanks for coming on the podcast.
Thank you. Have a good day.